In our last few lessons, we looked at properties of logarithms, and we spent some time rewriting logarithmic statements as equivalent logarithmic statements. And we were doing that to get us ready to solve logarithmic equations. As you're solving a linear equation, for instance, if I have 3x plus 1 equals 5x, I know that I can write an equivalent statement subtracting 1 from each side, that those are equivalent statements. And then I know that if I have 1 minus 1, that's 0. So this is an equivalent statement. And then I can subtract my 5x from both sides. And I get negative 2x equals negative 1. And then I can divide both sides by 2 and get 1/2. And what I'm doing at each step of this linear equation is I am doing mathematical processes that don't change the equation. And that's what we spent the last 3 lessons learning how to do, how to write equivalent statements with logarithms that do not change the equation. The first type of equation that we're going to look at with logarithms is that when there are not logarithms in every term. So to solve log equations, when there are logarithms in some terms, but not all. So our process, if we have an equation that looks like this, and with these we are actually solving. We're trying to find the value or values of x that make the equation a true statement. So if we have the logarithm base 6 of 2x minus 4 equals 3. So we're trying to solve for x. And we see that this is the type of equation that we're looking at, where we have logarithms in some of our terms, and then we have just numbers in some of our terms. Our first step, which we don't actually have to do on this one, but our first step is going to be to get all logarithms on one side of the equal sign, and all numbers on the other side. And this one already has that. Our second step is going to be to rewrite with a single logarithm. If I had more than one logarithm over here on the left-hand side, I would have to use the processes that we used in the last couple of lessons to rewrite as a single logarithm. In this problem, it's already a single logarithm. Our third step, and this is going to be the big step. This is going to be what we have to really remember when we are solving logarithmic equations with some logarithms and some numbers. And we have to remember that if I have a logarithmic equation, logarithm base a of b is equal to c, that is exactly the same thing as the exponential statement of our base a to the c power is equal to b. So on this step, we are going to rewrite as an exponential equation. So let's go ahead and do that. I want you to try to rewrite this equation right here as an exponential equation. Our base is 6. Our exponent is 3. And that is equal to 2x minus 4. And what we've done is we have converted an equation that was a logarithmic equation to an equation that is now just a linear equation, because we can find 6 cubed on our calculator, or just multiply 6 times 6 times 6, and we get 216. And now we just have a nice linear equation that we can solve. Go ahead and do that for me. Pause the video, solve the linear equation. And we see that we can solve this using our linear process. Add 4 to both sides, divide both sides by 2, and we have that x equals 110. So our fourth step here is to solve the resulting equation. And we're going to see that we have a fifth step as well. Remember when we are looking at a logarithmic equation that our domain here, when we're taking a logarithm, our domain is 0 to infinity, not including 0 and no negative numbers. So we have to make sure here that when we plug the x back in, and it's not the actual value of x, it's after you plug x back in, make sure that all of your arguments, in other words, all of the things you're taking the logarithm of, are positive, not including 0. So if I look back on my problem here, I have x equals 110. It doesn't matter what x is equal to. What matters is when I plug x back in to the argument. So we have 2 times 100 minus 4. And it really doesn't matter what it is as long as it's positive. But we have 200 minus 4 is 196, which is greater than 0. So this is a solution. So this is going to be our process for finding x, solving for x, when our logarithmic equations have some logarithms, but then just some numbers, don't have logarithms in some terms. Let's look at another example. Solve common logarithm of x plus common logarithm of x minus 30. And I know this is a common logarithm because there's no base. Anytime there's no base written, that's an understood base 10, which is the common logarithm. So I want you to do the first 2 steps here. I want you to get all of the logarithms on one side, all the numbers on the other side, and then I want you to see if you can rewrite the 2 logarithms on the left here as a single logarithm using our principles of logarithms that we learned in the last few lessons, which I have written here. Pause the video and do those 2 steps. All right, our first step is to get all of our logarithms on one side and all of our numbers on the other side, and we see that we already have that on this one. Our second step is to rewrite the left-hand side here, rewrite our two logarithms as a single logarithm. We have the same base, our understood 10, so we can combine them. We have addition in between, so that means that we're going to multiply our two arguments. And over on the right-hand side, we still just have equals 3. We didn't have to combine anything there. This whole thing, x times x minus 30, is our argument now. So our third step in our process here is our important thing here, our big thing that we need to remember is to rewrite as an exponential equation. And remember that we have an understood base here, base 10. So I want you to rewrite that logarithmic equation as an exponential equation. Pause the video and do that. So we see our base is 10, our exponent is 3, and that is equal to all of this, x times x minus 30. I want you to go ahead and try to solve this equation. That's our next step, solve. And we're going to see that this is going to be a quadratic equation because our first step is to distribute the x on the right-hand side. And don't let this 10 cubed confuse you. 10 cubed is just 10 times 10 times 10, which is 1,000. So go ahead and distribute the x, get your quadratic equation, and then use our quadratic process, which is to get it in standard form, equal to 0, keeping the x squared term positive. Try to factor. Pause the video and go ahead and finish solving this equation. Okay, if I distribute the x times x is x squared, x times negative 30 is negative 30x. I see that it's quadratic, so I want to get equal to 0, keeping the x squared positive. So I subtract the 1,000. I look for any common numbers, which there aren't any because this is already an understood 1. And then I try to factor. And because we have a 1 as our coefficient, we can just think two numbers that multiply to give me negative 1,000 and add to give me negative 30. And I see that those are going to be minus 50 and plus 20, because 50 times 20 is 1,000. To have a negative here, one has to be negative and one has to be positive. And the 50 needs to be negative to have my negative 30. So I have x equals 50 and x equals negative 20. But don't forget that we have to double check that if we plug the 50 and the negative 20 back in to the original equation, that each of my arguments will be positive. And it doesn't matter that I have a negative 20 here. What matters is if I plug it back in and have a negative. But when I plug negative 20 in for x, obviously that's negative 20, so I can't use that one. If I plug 50 in, I get 50, and then 50 minus 30 is 20, so the x equals 50 is my only correct answer. So be sure to check both answers. Make sure that your argument is positive. You could have both work, both don't work, one works, one doesn't work, but be sure to check. So on this one, we have the solution x equals 50. Let's look at another one. All right, and on this one, we have a similar problem. We have logarithms in some of our terms, numbers in some of our terms. So our first step is to get all of our logarithms together on one side, all of our numbers together on the other side. Our second step is to rewrite the logarithm as a single logarithm, and then rewrite as an exponential equation. Go ahead and do the first two steps. Pause the video, do the first two steps, getting all the logarithms together and rewriting as a single logarithm. And then we'll look at the next step together. To get this as a single logarithm, we have a minus sign. We notice we have the same base. So we can write logarithm base 3. And using our logarithmic principles, we see that if we have subtraction, we're going to rewrite our arguments with division. So we have x plus 1 divided by x. And then the 3 just follows down. Now we need to rewrite this as an exponential statement. Pause the video and do that. And our base is 3. Our exponent is 3, so we have 3 cubed equals our argument, x plus 1 over x. 3 cubed is just 3 times 3 times 3, which is 27, equals x plus 1 over x. Now, this is a rational equation, and we learned how to solve rational equations in a previous lesson by multiplying through by the least common multiple. And then we're going to see that that will cancel the x, and we'll end up with a quadratic equation, which we can solve by factoring and get 2 solutions. Go ahead, eliminate the denominator, solve your quadratic equation, and then turn the video back on. Our LCM here is just x, so we're going to multiply by x on both sides. That will cancel the x, and we'll be left with 27x equals x plus 1. Oh, and I said this was going to be a quadratic, but it is not because we canceled the x. So we can just use linear methods, and we have 26x equals 1, x equals 1 over 26. But don't forget we need to check. And again, we are checking to make sure that if I put 1 over 26 in for x here and for here, we get a positive argument. So 126 plus 1 is positive, and 1 over 26 is positive. So 1 over 26 is our solution. In our next video, we're going to look at how we solve logarithmic equations if all of the terms have logarithms in them. And we're going to see that we use a completely different process. But just to reiterate here, if some terms have logarithms and some do not, The big step is going to be rewriting as an exponential